Hello everyone, I'm Hari Prasanna Das. I'm a PhD student in Department of Electrical Engineering and Computer Sciences at University of California, Berkeley, and I'm also a member of Climate Change AI. Today I'll be presenting on tackling climate change with machine learning. So climate change, as all of us here know, that is an effect that is widespread all around the world, and it has increasingly severe effects such as storms, droughts, fires, and all of those extreme events. And climate change has uneven impacts on the society, and we have many governments around the world working towards different goals, such as net zero greenhouse gas emissions by 2050, and there is other organizations like UN Intergovernmental Panel that lay out some goals to have net zero greenhouse gas emissions by 2050, 2030, and there you have been hearing a lot. But still, all the emissions that happen from greenhouse gases are still increasing every year. And for that reason, climate change mitigation and adaptation approaches are extremely needed at the point. Now, coming to machine learning, we have machine learning as a group of techniques that automatically extract patterns from a large amounts of data. And it's a very powerful tool, as many of us here have known and have worked with it, right? So machine learning has both strengths and weaknesses, and I'm just trying to cover the basic strengths and weaknesses of machine learning so that we all here are on the same page in terms of what the applications that we talk about in the later slides. So machine learning has different strengths. It scales human insight by analyzing patterns in large amounts of data. So for example, if I am given a task to do and to analyze, let's say, terabytes of data, I'll completely be tired and I might not be able to do it in my whole life, right? But machine learning systems are extremely fast and they can scale large amounts of data in a smooth manner. Machine learning is good in optimizing complex systems. It's good in generating new or sometimes derived, that is new data or derived data from other sources of data, and integrating with other methods. For example, there are ways to do machine learning along with physics. So there is domain and physical models that can be deployed along with machine learning and domain knowledge. But it also comes with limitations, such that if you put garbage in, you get garbage out. And it also inherits the biases in data or design or use. So machine learning systems inherit the bias that comes from the person who is designing them. And machine learning assumes that the patterns are persistent, which means whatever it has learned in the previous times, it assumes that that will stay the same in the future. So it's sometimes difficult when we are talking about long-term forecasts. And the other limitation is that it finds correlation, not causation. Of course, with some modification, you can try to find causation and if there is a causation, cause and effect or not. But in general, machine learning algorithms find correlation. So motivated by all this, a few years back, a group of people from different universities in the world and organizations in the world came up with this paper called Tackling Climate Change with Machine Learning that covers the applications of machine learning to tackle climate change in different facets of climate change, as we'll discuss in the coming slides. By the way, this paper is online, and if anyone wants to take a look at it, please search for this name in Google and you'll find the PDF version of this paper. Now, in this paper, the areas that are covered from the climate side includes mitigation or climate change mitigation, which has electricity systems, transportation, buildings and cities, industry, farms and forests, and everything. So in this vertical, we try to mention methods that are used to mitigate climate change in these individual areas. We have climate change adaptation, which comes with the assumption that climate change is happening and it's real, and how do we adapt our society to the climate change effects, right? And in this, we have climate prediction, and we have societal impacts and solar geoengineering. Then one of the other verticals we have in this paper is tools for action, as in what you can do as an individual or as a group. What can you do collectively or individually to work towards tackling climate change? Now, from now, I'll cover some sample applications in different domains of climate change, and we'll see what's the need of machine learning in each of these domains, and who are the partners that we need to work with in the particular application of climate change. Let's start with my own research area, that is buildings and cities. So we'll see how machine learning can be used in buildings and cities. So in building, buildings is nothing new to anyone here. We all live in buildings, and in fact, we spend around 90% of our time either in commercial or residential buildings. So the energy that is consumed in buildings is huge, and there is a need to optimize the energy that gets consumed in buildings. So the need is to have increased energy efficiency in building, both existing and new. And the machine learning tools that can be used here are smart equipment control with machine learning based tools, and with some base measurements such as insulation, which means you need to insulate your building first before moving into implementing any machine learning solutions. And these are some different areas in buildings where you can implement machine learning systems. One of the key area is HVAC, which is heating and cooling, because a lot of energy gets spent in heating and cooling. We have lighting, we have industrial equipments, and in this space, the stakeholders are building managers and the city planners and the equipment manufacturers. Let's go through one of my own projects in this domain. So we have, when we're trying to control a building, we need to have something called human-centric building control, where we have building control algorithms designed and building that is operating based on the input that comes from actual people that live inside the building, right? So the way to do that is to have to understand factors that govern the thermal comfort, and thermal comfort means how comfortable they are in the immediate thermal environment of a building, and put that and get those informations from individuals by putting sensors around their bodies, and the sensors that collect are the parameters collected by the sensors are temperature, humidity, and heart rate, and all of those parameters. And eventually we use machine learning to get those data and to predict thermal sensation based on that data, right? So thermal sensation or thermal preference, if we are able to predict when an individual would feel warmer, cooler, or no change in the temperature, you will be able to put that into building control, and you can control the building in an efficient way. And by doing this, the human that that inhabits the building will be happier. At the same time, you are able to optimize the energy use. But in this, there is a challenge. The challenge is that we have high class imbalance in building datasets that hampers accurate and robust prediction by machine learning algorithms, right? So we often have very less data for feeling warmer or feeling cooler cases, as compared to the case where the occupant prefers no change in their temperature, right? So the need here is to have better prediction under those class imbalance conditions. So I designed synthetic data generation methods where we put the existing class imbalance data and learn the data distribution, and then generate more synthetic data for the low frequency classes, so that we can augment it along with the real data and can make machine learning models more robust. We have farms and forests where the need is to model emissions and land use attributes for simulations or policy decisions. And the different machine learning algorithms are remote sensing. And by remote sensing, we collect data from satellite, aerial, or drone imagery, and those images are used for different purposes, such as object detection, semantic segmentation, spatiotemporal forecasting, and whatnot. And in this case, also the stakeholders are farmers, NGO, different government programs, and different startups that focus on agriculture. So as you can see, in all these applications that we're talking about, there is a need for machine learning. And of course, when we're trying to implement machine learning algorithms, we should collaborate with the stakeholders, as we are mentioning. We have transportation, and in this particular slide, the transportation that we focus on is freight transportation, or not passenger transportation, but freight, which is transportation of goods. So in that industry, we have the need to decrease the emissions that come from sourcing of goods, as in we have different trucks, buses, or aircrafts that transport the good, and we need to decrease the emissions that are associated with it. So the machine learning technique that exactly comes to help in this case is we can have clustering algorithms that can cluster the suppliers. We can have improved routing and auction mechanisms, and we can also predict the demand so that we can reduce the overproduction, right? And in this case, so essentially in this particular transportation case, we are trying to make the supply chain better, right? So the stakeholders in this case are logistic management companies, which essentially companies that manage the transportation of goods. We have rail or freight companies, which manage the transportation of goods, or sometimes in the transportation industry where we have passenger transportation, we have trains, buses, or we have like Bahn in Germany, and like all these different companies. One thing to be aware in this case is something called Gibbon's paradox, and Gibbon's paradox says that if you over optimize the system and you make it really good, then that leads to overuse of the system and eventually not leading to any benefit that you originally try to get from the system. So in the beginning, if you optimize the system so good, like if you optimize the transportation supply chain so good, it might lead to overuse of that system, and eventually the emissions that are associated with those systems are the same. So you are not decreasing anything. So in these cases, it's very important to make Gibbon's paradox, to make sure that the Gibbon's paradox case doesn't happen. And to do that, you can design your algorithms in a proper way by designing proper loss functions, designing proper target functions, and all. We have electricity systems where the goal is to forecast supply and demand of electricity. So essentially, we are trying to schedule when and how much we will be generating electrical power. And in this, the machine learning techniques that are commonly used or can be used are short and medium term forecasts. And essentially, we have historical data of electric power, and we have some physical model of the system of the grids, and we can use machine learning to predict how much power a city or a town or a consumer would need, so that we can properly plan the generation of electricity. And by knowing all this, you can also plan to incorporate renewable resources into the grid, so that the overall emissions gets reduced. In this case, the stakeholders are system operators, power producers, demand aggregators, these stakeholders mainly you can think of them as the stakeholders that generate the power and the stakeholders that distribute the power, essentially. In this case, some important considerations are to incorporate system physics and goals. So in this case, power, when you generate and you transmit, it goes through some transportation modes such as electrical lines. So in those cases, there is some system physics that is existing in those systems. So it's very essential to make sure that the machine learning algorithms also obeys those rules, right? So we need to incorporate those system rules or system physics in the machine learning algorithms. And in this case, it's also very important to characterize the uncertainty to understand that how much error or how much uncertainty will be there in the prediction of the algorithm. And to have interpretable focus, which means, let's say your machine learning is giving some output, the machine learning should, the output should be comprehensible. Like you should know why that output came and how that output is related to the input that you fed the machine learning algorithm with. We have other climate predictions, such as you want to accelerate climate simulations so as to understand when different climate events would occur and what's the current state of different parts of the natural resources of the earth. And in this case, the need is to have efficient, accurate climate simulations. And the machine learning tools that can be used here are essentially what they do is they improve the portions of simulations, and they can do that by using approximate cloud physics to reduce form models, we can have, we can gather data about ice sheets and sea level rise from different satellite imagery using remote sensing. And those images or those different data points are fed into machine learning algorithms to improve the climate simulation. The stakeholders here are, climate scientists and local governments that, work in climate predictions. So in all these themes that I was talking about, we saw some recurring themes. For example, we saw forecasting, which was, which came in the solar power section, in extreme events and carbon prices. And sometimes we also saw, in many times we also saw data mining and generation, where we are trying to understand the data better, and in cases where there is need of generating more data, we are trying to generate more synthetic data, right? So in those cases include disaster response or urban planning. And also we also saw in some cases there were remote sensing, where we are trying to get data from satellite imagery to understand different facets such as emissions or infrastructure data or deforestation, right? We also have different approximating time series intensive simulations. So we have simulation that is there in almost every application case. And to have those simulations in a better way, we also have proposed machine learning algorithms, and particularly we did that in the climate and energy case. We also have material science research, for example, research into batteries, perovskites or nuclear fusion, where we need accelerated experimentation and where machine learning is also being proposed. So these are kind of the different recurring themes that we saw while discussing different machine learning applications in climate change. We also had optimizing systems. Just to add some more cases, we had systems in precision agriculture, heating and cooling of buildings, and in those we had machine learning algorithms that were put into optimizing the different systems. We also had predictive maintenance, where we wanted to understand when the system would need maintenance, and so that we can do it preemptively. And those cases were there in natural gas pipelines, resilient infrastructure, and everything. So while designing machine learning algorithms for tackling climate change, there are some important considerations that we need to focus on. And the primary consideration is that machine learning is not a silver bullet, which means you can't just take a machine learning algorithm, put it anywhere, and you just expect that it will work. So to have machine learning algorithms work, you need to have some groundwork done, which means that you need to have your bases cleared before you put machine learning. For example, this like very applicable machine learning is one part of the strategy. So I was trying to give the example here, which is, think of a building where, you have extreme climate outside. It might be, cold climate outside, and you need to have some insulation in the building. So you can't have, zero insulation and still put some machine learning algorithm to optimize the system. That will be highly suboptimal. So you need to make sure the bases are clear, which means you have proper insulation, and then you can design some machine learning algorithms to, optimize the energy use or optimize the temperature or the climate inside the building by making sure that the physical material like the insulation and all those base cases are completely taken care of. Then in the pathway to impact, which means you have machine learning algorithms to be used towards a particular impact, you have a whole long process, and in that whole process, machine learning is just one part of the whole process. So as you can see here, if you want to implement machine learning for some particular algorithm or a particular implementation case, you need to identify the domain first, and then you need to scope the project as in what particular things you want to do. Then there is the development phase, then there is the analysis phase, and then you go to deployment. And then once it is deployed, you want to monitor it to make sure that the effects are as you have expected. And in this whole space, the machine learning part comes exactly in the development phase, where you have some data and you design a machine learning systems based on that data. So essentially, machine learning is one part of the whole system, and it's not the whole system itself. So essentially, we need to consider the system level and downstream effects before directly jumping into some designing machine learning algorithms. And in that system level and downstream effects, we have life cycle impacts. For example, the Gibbons paradox that we talked about. We have equity measurements where we need to make sure that the algorithms or implementation that we design are equitable across different communities. And also the work needs to be driven by relevant stakeholders. So for example, you have transportation systems, you have different transport operators. They need to be taken together while designing some machine learning solution, so that your solution is sound in terms of the domain considerations that needs to be taken care of. So we need to pull in different experts of the domain and different deployment partners, so that together with them we can design machine learning algorithms, and of course the end users. So having all those, having known the different applications, different considerations, and different recurring themes. So now that we are ready to do some machine learning for climate change mitigation, so what is the roadmap for action, right? So the roadmap starts with learning about different ways to get involved. So all of us are here and we are learning about different things from each other. So one of the key things to learn from each other right now is to different ways that you can get involved to tackle climate change, and that need not be AI or machine learning, right? Then to collaborate with others with different perspectives, because everyone comes with their own perspective, and a diverse perspective is the best perspective, as I believe. So it's very useful to collaborate with others, while designing algorithms in this particular space. It's also essential to listen to what other collaborators or stakeholders say, because they are the domain experts, and by listening to them and by designing algorithms based on what they need, you can, in that case only, you can design algorithms that can make some real impact. Deploy and ensure a path to deployment. So a lot of algorithms that even we academics that we design are just experimental. Many of them don't see the light of real implementation. So while designing, it's highly advised that you keep in mind that whatever you are designing, how that can be taken into the real life and how that can be implemented in real world applications. So with all the different considerations about climate change, as we mentioned, I am now happy to introduce you this organization that I'm part of, called Climate Change AI. So Climate Change AI is an initiative to facilitate work in the intersection of climate change and machine learning. And we have different programs that we run as part of Climate Change AI. I think all of them might be useful to many of you here. So it's worth mentioning a little bit more about Climate Change AI. So in general, all of our resources are at this website called www.climatechange.ai. And we run different programs, for example, virtual happy hours, we have newsletter, tutorials, wiki, talk recordings, and a lot of other, offerings that we do. And particularly for students, we always, encourage them to contact potential mentors and collaborators in this space, and to take classes in multiple disciplines. For example, I am during my undergrad, I took a lot of courses in power systems, and during my grad school, I took a lot of courses in machine learning. And now I'm able to combine the best of both worlds by combining machine learning to tackle different challenges in the building or energy sector. So it's very essential that you take multiple classes and learn a lot of different perspectives. And for professionals, we encourage to join community meetings and public engagement events. For example, like if you have events to for greener roads or bicycle lanes, all of those things, you should try to join those community meetings, so that you can contribute towards the fight to tackle climate change. And to leverage your network, try to find who in your network is working on some really cool applications in climate change, tackling climate change, and try to talk to them and try to understand what they're doing. Now, I'll just cover some resources that Climate Change AI provides. So we have this platform called Community Platform, where we have people that are registered here, and you can join this platform, and you can find if you are looking for collaborators, if you're looking for funding opportunities, or if you're trying to hire, or you are trying to get hired in the space of machine learning, and climate change, we highly encourage you to join this community that we have built. And you can go to this link, community.climatechange.ai, to access our platform. We also have, as part of the community platform, we have something called Climate Change AI Directory, which is the list of people that are part of that are working in the space of climate change and machine learning. And you can find your collaborators there, or you can connect with them, and you can post if you are hiring, or see if somebody is hiring. You can contact them. So it's like a place where you get to socialize with others in the same space as yours. And to visit this, you can go to directory.climatechange.ai. We have a CCAI newsletter that we release every 15 days or every month. The newsletter has a lot of different offerings. We post call for submissions for workshops and conferences. We have funding opportunities. We have projects and courses. We have readings, jobs, and a lot of other offerings that we have. To sign up for newsletter, please go to climatechange.ai/newsletter. And we also have happy hours where you can join, and in an informal setting, you can talk to other people in this space, and you can build connections. And to note here, the next happy hour is on February 1st. So if any of you would like to join, or so the next happy hour from today is on February 1st. So depending on when you are seeing this, you can go to our website, climatechange.ai, and see when the next happy hour is, and potentially join the happy hour. We also have webinars that goes on, where we focus and we invite a lot of different speakers in this space of climate change and machine learning. So there are a lot of opportunities that we offer as part of Climate Change AI, and I encourage you to check some opportunities out. So finally, we have our website at climatechange.ai and our Twitter handle at climatechangeai. So I hope you enjoyed my presentation. And if you have any questions, I'll be happy to take via email. And my email address is hpdas@berkeley.edu. Thank you.